Hello, so our experiment is about superhydrophobic prosthetics and their ability to prevent corrosion by me, Caitlin.
Me, Avi.
Me, Aaron.
I'm Nadia.
I'm Estelle.
And our goal or main objective is to create a superhydrophobic coating that will prevent corrosion of prosthetics. And to give some background on prosthetics, they are made out of titanium, aluminum, and other metals. And they are medical implants, such as dental implants, to improve mobility, manage daily activities, etc. However, there are some current issues with prosthetics, such as the biomaterials that make them up. They should contain sufficient mechanical strength to avoid fracture. However, the repetitive exposure to impure water contributes to corrosion. And in addition, the degradation of metallic implants occurs when placed in hostile electrolytic environments that can lead to postoperative implant-associated infections. And last but not least, since water is able to seep into most implants and prosthetics, this then shortens the longevity of the implants and in addition to the stability. And if you look at the photo right there with the two prosthetics submerged in water, some prosthetics are in fact waterproof, but they can go up to about $50,000 and last roughly about 3 years. So this then leads us into our areas of investigation, and in the scientific community, they're trying to figure out how to develop superhydrophobic implants that are bacteria resistant and a surface modification of the biomaterials, such as coating techniques, which makes use of the superior properties of nanomaterials that lead to a better, improving biocompatibility.
So in contrast to a regular hydrophobic surface, a surface is characterized as superhydrophobic when a water droplet is able to fall on it and form a contact angle between the water droplet and the surface that is on that exceeds 150 degrees. So all levels of hydrophobicity are measured by a contact angle, which is the angle made between the water and the surface that it's on. And superhydrophobic surfaces can only be made if they are coated with a hydrophobic substance and are roughened, and if the surface is roughened at the nanoscopic level. So all of our coating that we're using in our experiment is superhydrophobic since we need our materials to be water resistant.
This then leads us into our important question on how does superhydrophobic coating of metals respond to corrosion in water environments with varying pHs? And we chose a varying pH from 5 to 9 because this is the range of pH of water that is naturally found across the world. And then our hypothesis is that we hypothesize that the superhydrophobic copper that is coated in DCT, titanium dioxide, and never wet will undergo minimal corrosion, whereas the uncoated copper in the pH 5 that is a solution with nitric acid and water will undergo the most corrosion.
So we used nitric acid in our experiment to lower the pH of the water that we submerged our copper samples in, because the copper we used reacts with nitric acid and is highly corrosive, and the nitric acid is highly corrosive to the copper. So the equation above shows the oxidation reaction that takes place when copper is in the presence of nitric acid. And we predict that this reaction will occur the fastest in our uncoated copper sample because that's the only sample that does not have a superhydrophobic barrier between the pH solution and the copper surface. So some potential medical and economic impacts that can result from creating a superhydrophobic surface for prosthetics include increased longevity of the prosthetic, reduce infections related to the prosthetic, and reduce costs because if we have a superhydrophobic coating for the prosthetic, people can buy prosthetics made out of cheaper material rather than expensive waterproof prosthetics and just spray the superhydrophobic coating on top of it.
So in our experiment, we used 3 different coatings, and each of these hinge upon the fact that we use nanoparticles in order to induce superhydrophobicity, which basically stops any kind of water or acid or anything else from touching the metal on the inside. So our first coating was a DCT coating, and in order to do this, we first took our copper slides, sanded it down in order to remove the oxide layer, then submerged it in silver nitrate in order to create silver nanostructures, and then submerged it in DCT in order for the DCT nanoparticles to bind and with their nonpolar tails create the superhydrophobic layer. The next coating we use is titanium dioxide, where we synthesized our own titanium dioxide nanoparticles. And this is by soaking it in acetic acid and by grinding it down for about 25 to 30 minutes. And in this time, these rather large titanium dioxide particles go into their nanostates. And in order to keep them there and stop it from aggregating, we added an oleic acid capping ligand in order to preserve the unique nanoscale properties. And finally, we use the Never Wet spray, which is a commercially available spray, in order to compare with industry standards and to see how our products stand up to what's there in the market already. And finally, our control for this whole experiment was uncoated copper, as this would provide the best baseline in order to see how good our coatings are, and as we can see how much corrosion occurs before and after submerging it in different pH solutions. And as you guys can see, that is our uncoated copper. It looks kind of smushed because uncoated copper is hydrophilic, whereas you can see the Never Wet, the DCT, and the TiO2 have a lot better beating up because they are superhydrophobic surfaces.
So as we could not really measure the contact angle just by eye, we decided to use an optical tensiometer, which allowed us to take zoomed-in pictures of the water droplet on the hydrophobic surface and then measure the contact angle by setting points on a computer. And so those are the pictures that we took. As we can see, the encoding copper has an angle of 84.31. So this shows that it is slightly hydrophilic. And the other coatings, the Never Wet, TiO2, and DCT, all have super hydrophobic angles, and the DCT is nearly superhydrophobic. And the red lines that we unfortunately cannot really see were the points that we set to measure the contact angle. And we also measured the mass to determine the corrosion as to quantify the corrosion. And as we can see it in coated copper, because it has nothing on it, it has a very small standard deviation. But the Never Wet, because it was a spray, the coating was uneven, and that caused the standard deviation to be quite large and maybe affect the results.
Okay. So we created water of different pH levels by adding nitric acid to lower the pH of the water and sodium hydroxide to increase the pH. pH was recorded constantly whilst adding the acids and bases by the use of the pH meter, which can be seen on the right. The dilution of acids and bases allowed us to obtain pH levels of 5, 6, 7, 8, and 9, which we use for experiments. So the next step in our experiment was to submerge our copper pieces into each pH solution we made. For each row, you can see a different coating that we used for the copper, and each column has a different level of pH. Furthest left being 5, going up one at a time, all the way to the right to 9. They were submerged for 18.5 hours, although this picture was taken only 5 minutes after we submerged them.
And so after leaving the samples in for 18.5 hours, we measured the contact angle again. And what we found is that DCT remains superhydrophobic, as we can see on the graph. So it is the best coating. And copper, the encoded copper, had the lowest hydrophobicity and the highest standard deviation. So some of the samples were really hydrophilic and corroded a lot. And so then we also plotted the contact angle against each pH. And what we found is that at pH 5, there was a large decrease in contact angle before and after submersion. So that might mean that increased acidity increases the reduction in contact angle and thus increase corrosion. And when we zoom in to look at only DCT and uncoated copper, so the best and G control, we can clearly see that there is a drop in contact angle at pH 5, but also that at pH 7, this is where there's the least change, and that might be caused by the fact that it's just water and there's no acid or base in the solution.
So after calculating the % change in mass for each copper sample, we found that the difference between the final and initial masses of the copper pieces were not significant enough to indicate corrosion. However, the uncoated copper, the never wet, and DCT coated samples had a very slight increase in mass, while the TiO2 copper had a decrease in mass. And we think that this happened because when the TiO2 copper pieces sat in the pH solutions overnight, the TiO2 film on top of them degraded, therefore accounting for the decrease in mass. So similarly, when plotting the mass change of the copper samples against the specific pHs they were submerged in, it was apparent that the pH did not significantly affect mass change except in the TiO2 sample, like I discussed in the last slide. However, the mass change results for the TiO2 samples were most likely anomalies that resulted from the degradation of the TiO2 film after leaving it in the acidic pH solutions overnight. However, more trials would need to be performed to confirm that these were in fact anomalies.
And we can see that our uncoated copper in both the pH 9 and the pH 6 solutions have corrosion. As you can see that the shiny copper oxide layer has completely gone. Further, there are darker spots which indicate corrosion as well. The DCT is actually not corroded. That's actually just the silver on the coating. So the metal was more or less unharmed, as we could tell from our mass data, and the never wet and the TiO2 also held up pretty well. However, we did have a couple of sources of error during our experiment, and the first one would be related to our TiO2, because our TiO2 on application and after it dried, it started cracking, which basically left holes for the solutions to go in and actually interact with the copper, thus corroding it. And so in the future, we should probably look into a different capping ligand, which can give our solution a different viscosity so that it can actually spread well and not crack. The other aspect of the TiO2 is that it actually, the suspension liquid or the suspension agent that we used was acetic acid, and that actually started reacting with the copper. As you can see, the copper slides in the picture are actually blue, whereas TiO2 is actually white. So maybe in the future we need to look at a different suspension agent that doesn't actually react with the metal it's coating. Another source of error was that a couple of the surfaces that we were testing were actually so super hydrophobic that we couldn't physically put water droplets on it in order to check the contact angle. So in the future we should probably look at oh my, is this playing? Oh, it is. All right, yeah, you guys can see how the water droplets roll off. And so basically in the future we should probably be able to get slides which are perfectly flat so that we can actually measure our contact angles.
Okay, so we conducted a further study with the nitric acid to represent long-term corrosion in the limited time frame that we had, which is 2 days. We can see that the nitric acid in fact reacted with the uncoated copper, DCT, and TiO2, except for the never wet. And the TiO2 and the DCT in fact became hydrophilic, but the never wet stayed hydrophobic.
And so after submerging them also in about 18.5 hours, we did a UV visible spectrophotometry, which basically means that we recorded the wavelengths at different absorption, and so we could really plot a graph like this. But the only problem was that the solutions that we took were too concentrated, so we couldn't actually plot the graph and record the absorption. And so in a further study, we would have to get more dilute solutions in order to get a better graph and actually be able to observe the corrosion through the absorption spectrum. So we concluded that DCT was the best coating to reduce the corrosion of prosthetics, and we came up with that conclusion because DCT was the most superhydrophobic, and so it was the best to prevent short-time corrosion. But we also concluded that uncoated copper was the one who corroded the most at pH 6, which we originally thought was pH 5, but when we look at the loss of superhydrophobicity, it was actually at pH 5, so we can say that our hypothesis is partially correct. And the TiO2 coating that we did was not really effective, so we would need to do further tests to get a better and a more even coating. And overall, we can say that the coating produces a better performance in terms of reduction of corrosion and preventing loss of superhydrophobicity for all the coated samples, which is really promising for future research.
All right, and now some improvements on our experiments. So due to our limited time frame, we weren't actually able to simulate longer periods of time in which we could put our metals in and check our surface coatings. So a possible improvement could be that we can maybe increase the time that we leave our surface coatings in solution from because in this experiment we left it for around 18.5 hours, but we could leave it over weeks and maybe months and collect data, and that might be that might lead us in a different direction. Further, only copper was used because that was the most easily available metal that we could find. However, prosthetics are not actually made of copper, so we might have to look into silver, aluminum, titanium, and stainless steel, which are all materials that prosthetics are actually made of. Another aspect of our experiment, which kind of changes our conclusion, is that the NeverWet is actually not ingestible, so we can't use it in prosthetics, which are implants. So, for example, dental implants, you can't put them in your mouth because of ingestion problems. And so maybe finding some solutions which are actually non-harmful for humans would be another direction we can take this experiment in. And finally, our titanium dioxide coating was not efficient, both due to its suspension agent and its capping ligand. So further research needs to be done in order to find more efficient alternatives for them.
Thank you very much.
Thank you.
So you use 3 different materials. Some they have chemical names like TiO2, but some they have commercial names. Are there a difference between these materials in terms of how easy to obtain, how cheap or expensive they are? So in terms of practical use case.
Right.
Yeah.
Can I take this? Or
Sure,
you got it?
take it.
Okay. So the DCT and the titanium. Okay, titanium dioxide is actually what you find in paint, so it's actually relatively cheap and it's not all that expensive. The DCT, on the other hand, is a little more hard to find. The commercial NeverWet sprays actually have a blend of aluminum. I think there's iron in it. Silica and
I think acetone.
Acetone,
Yeah.
right? And so I don't actually know how they produce that and what the costs are for that. But for the other two, they're actually not that costly. And if we look at it in the grand scheme of things, instead of buying waterproof prosthetics, which are $50K every 3 years, you can buy something which is under $10,000 and repeatedly apply these sprays, and which would probably not even reach $50,000 over the lifespan.
Yeah, and as we said, the NeverWet spray is just available in any store, so you can just buy that, but you cannot put it in an implant, so dental implants. So we were trying to find a solution, another solution that would work for internal implants.
So thinking about real-world applications, I was thinking about durability of the coatings from an abrasion resistance standpoint. Is that something that you considered and showed up? It seemed like some of that TiO2 might have been subject to some of that. And one of your early slides had, looked like a hip replacement piece where that could be applicable as well.
Yeah, so we didn't really look at abrasion, but the TiO2 coating definitely just fell apart, so it would not be sustainable for a long time. So we need to find a way to coat it and make it an even surface so that it actually resists corrosion and abrasion maybe, but that would definitely be something to test.
Further, our experiment was mainly like targeted at how can we decrease corrosion. So we didn't actually have like the time nor the materials to actually research how to make these surface coatings like hard enough to like withstand like a heavy usage. So we were only looking at the corrosion aspect of it.
Thank you.
It's a great experiment. I'm just curious how good you maintain the pH. Did you measure it, before and after the experiment? Is there any pH change? I understand you use nitric acid and sodium hydroxide to create the pH of the water. Thank you.
Okay, so
Try to mix around you answering the question. Let everybody answer the question.
Okay, so what we basically did was we took distilled water and we added either the acid or base to alter the pHs that we need. So we basically just diluted the acid with water until we got the desired pHs that we needed for the experiment.
In addition, we used a pH meter just to be precise and accurate with our pHs to make sure that they were right on.
Did you measure after the corrosion?
no.
In the wells?
No, we didn't really think about measuring the pH afterward. That would have been a very good idea. So in future research and experiments, we should definitely do that. Thanks for the, yeah.
That means I have to know how to turn it on.
Okay. No, it's for the live stream. You can't hear it if you don't have the mic. That's actually a really good point because the corrosion process can change the pH. So if it was long, you don't know. So first, a comment for everybody. Lots of people are asking questions, and people are saying, well, we didn't get to that. Of course you didn't get to that. You had 4 days to do the whole experiment. A PhD takes 5 years, and you had like a tiny fraction of a week. Of course you didn't get to tons of things. Don't feel guilty when you say, sorry, we didn't get to that. It's a short summer program. The whole first week we were teaching you like how to be a scientist. Then you got to actually do it for a short amount of time. Okay, so my question for you is, so you did an experiment that I thought was a great experiment where you dunked them in concentrated nitric acid. No prosthetic will ever meet concentrated nitric acid. Why was that a great experiment?
So basically what we wanted to do is that because we had such limited time, we wanted to put it in concentrated nitric acid to kind of represent the the repetitive exposure to nitric acid or to acidic water, and to make it just like in short time and to maybe test the resistance in like nitric acid, even if it's it won't be exposed to such concentrated nitric acid, but it's still useful to know if it can resist that much.
So that's right. But basically a thing to say is that more extreme chemical conditions is equivalent to much longer time at less extreme chemical conditions. And so when you don't have time, when something's supposed to last for years and you don't want to test it for that long, what you do is you make it a more extreme case and then you do a shorter amount of time. And you say, oh, a little time at these crazy conditions is equivalent to years at more normal conditions. And people do that for everything. Batteries, solar cells, bio things. And so that was a great example of what people do to test long-term stability when they are not that patient. Okay, another awesome job. And now Rita has some announcement.
Well, basically
basically just one announcement. So we're going to take a break for about 10 or so minutes. So everyone please relax. There should be some snacks outside, and we'll be back in town.
Thank you, everyone.